Alright, we've talked about polarity and how it's due to an imbalance in sharing, so unjoint custody of electrons due to a difference in electronegativity. However, the whole polarity thing, it does make a difference on the structure. So depending upon the molecular geometry or the VSEPR structure that's predicted, is going to determine whether or not it actually creates dipoles, whether or not you actually have those partial charges. Alright, so here's just another example of a polar bond. When you have hydrogen bonded to chlorine, chlorine is significantly more electronegative than hydrogen, so as a result the electrons are pulled more closely to the chlorine molecule, and so you're going to have a higher electron density around chlorine than you are around hydrogen. So as a result you'll end up with a slightly negative charge on chlorine and a slightly positive charge on hydrogen, and those slightly positive, slightly negative charges are called dipoles. And you can have a dipole that's positive or a dipole that's negative. So in order for a molecule to be considered polar, it has to have a dipole moment. And a dipole moment is just one of those partial charges that form due to the imbalance of electrons. So you don't have to make any calculations for this, it's all qualitative, but this equation just shows us how those dipole moments are created, so it's based upon the absolute value of the charge times the distance between the two poles of that molecule. So unlike the HCl, it would be the distance between the dipole on the H and the dipole on the Cl. So what you're concerned with then, in order to know if a molecule is polar or nonpolar, you have to know if the bonds within the structure are polar, and then you have to know the overall shape. So those two things play a role. So first we'll just look at one that we do know is polar. So on this molecule right here, of course the electrons are pulled towards the more electronegative chlorine. There's nothing to cancel out that pole, and so as a result this molecule is considered a polar molecule, and it will have a delta negative and a delta positive on either side. Let's look at another linear structure then. So here we have carbon dioxide, carbon bonded to oxygen. And if you look on your periodic table just to see the trends, you'll see that oxygen is more electronegative than carbon. So that means the electrons are going to be pulled towards oxygen on either side of the carbon dioxide molecule. So when you look at this, this is symmetrical, a molecule. The electrons are being pulled equally in either side. So imagine this like two people of the exact same strength pulling on a box. So if you have two people pulling on a box on opposite sides with the same strength, will that box move? No, it won't, because they're going to cancel each other out. Same thing happens with this molecule. If this oxygen is pulling with its electronegativity and that oxygen with its electronegativity, they're the same strength, they're opposite directions, it's symmetrical, so therefore this molecule would be considered a nonpolar molecule. Even though there's a difference in electronegativities, there's no pull of electrons, and therefore there is no dipole moment. Let's take a look at water. And so this water is drawn according to the VSEPR model, or pretty close. It's a bent structure, and so oxygen is more electronegative than hydrogen, so it will pull the electrons towards it. And let's use the box analogy again. Imagine two people pulling on a box. One is pulling up, and the other one is pulling over. Will that box move? Yeah, it'll end up moving in a net direction like that. So same thing with a dipole. You end up with a net dipole going that direction, and that would be delta negative to these two delta positives. And actually this delta negative, this dipole, would end up being double the charge of these two guys right here. Okay, so that'd be half of the value of that one, because it's those two added together to equal that one. So really, in order to figure out polarity, you have to know your VSEPR structures, because that's what determines whether or not a molecule is polar or not polar. If you look at BF3, fluorine is the most electronegative element on the periodic table, and so that means all of those fluorines are going to be pulling. And if we use our box analogy again, we're pulling from three identical angles. All these angles would be 120 degrees. And so as a result, they will cancel each other out, and so this would be a non-polar molecule. And here's a tetrahedral structure, and with this one we're going to have to kind of imagine it, because it's drawn 2D, but it is a four-dimensional structure. All the dipoles will be pulling towards chlorine. Chlorine's the more electronegative molecule, and so this would be like people pulling on four opposite ends of a box. It's not going to move. This would be a non-polar molecule again. Dipoles cancel out, no pull. However, it's not just the shape, it's kind of the arrangement of the shape as well. Here's another tetrahedral molecule. If we take a look at this one, so we've got carbon bonded to hydrogens and to chlorine. So carbon is more electronegative than hydrogen, which means that the carbon is going to pull the electrons towards it from the hydrogens, and then the chlorine is more electronegative than the carbon, and so it's going to pull carbon's electrons towards it. So for the box analogy, imagine a box with 3 people pushing on it and then 1 person pulling on it. Do those dipoles cancel each other out? Absolutely not. What you're going to wind up with is a region down here that's going to be delta positive, and then this region up here will be delta negative. So the electrons are pulled from the hydrogens to the carbons, then from the carbon up to the chlorine, and so this area down here with the hydrogens would be slightly positive, a dipole positive, and that area up there would be a dipole negative. And with this trigonal pyramidal structure, nitrogen being more electronegative than hydrogen, so it's going to pull the electrons towards it. And since this is not symmetrical, because we've got that lone pair up there, we're going to wind up with a pull overall that way. And so we're going to have a dipole negative, and this region down here would be dipole positive. So this would be a polar molecule. So something cool about this structure thing, so if you have 2 diatomic molecules that contain atoms from the same group in the same proportions, they will have the same shape, and both will be either polar or nonpolar. So since their shapes are identical, they're going to have the same polarity. So this can help chemists design new materials. So by replacing one group with another one, like if we took silicon dioxide, which is basically sand, so you use that in ceramics, and we replace silicon with tin, tin's going to be a little bit stronger than silicon is. This is a metalloid, and this is a poor metal. And so this guy right here would be stronger. So if we replace it, hey, it's going to be the same shape. It's going to have the same polarity. So it's going to bond the same, fit the same, but it's going to be a little bit stronger. And so therefore, chemists can use that property to make new materials stronger, better, or just work more efficiently.